So what we're doing now is figuring out what the angular momentum of a particle can be, even if the particle is just moving linearly. Let's do a little bit of math first. The angular momentum L of a particle is equal to R cross P. And here again, R, we must remember what R is. Well, this is where a particle is moving of mass m. So R is, again, the displacement from the axis of rotation to the point where the mass is stationed. So for angular momenta of particles, we again have to use this definition of R. Displacement from axis of rotation to point where mass is stationed. So we can express the angular momentum of a particle as R cross P, where P is just mv, and the cross product introduces this sign of the angle theta, where the angle theta is the angle between the R vector, the displacement from the axis of rotation to the point where mass is stationed, and the momentum vector P. Those are the two vectors we got to, again, put tail to tail to figure out the angle between them. Now let's take a look at how it is possible that a particle can have angular momentum. So here what we have is two skaters. Skater 1 is headed directly towards a pole. And they're going to try to grab that pole and spin around it. Skater 2 is headed at some distance d away from the pole. Again, we're going to use this moment arm concept. But the moment arm will basically be the distance from the axis of rotation, right there, that pole, to the line, and it's not strictly called this, but here's our velocity or our momentum vector right here. That distance from that line of action of the momentum to that axis of rotation, that can also be considered the moment arm d. You could also look at it as, it is in fact r sine theta again. Here's theta, the angle between the velocity or momentum vector and the r vector. And let me go ahead and add onto that vector, there's the arrow for it right there. Put them tail to tail, there's theta. The moment arm is equal to r sine theta as before. So that can be a helpful little equation. Now notice what will happen is this skater will just smash into the pole. They won't spin around it. But the skater that's moving sideways of the pole can grab on the pole and they will spin around it like that, maintaining their same angular momentum. So what this all means is as follows. If you are moving linearly, you can have angular momentum about a certain axis. Skater 1 has no angular momentum about this because the line of action of their momentum vector goes right through the axis of rotation. They will hit that pole and just stop. They will not be able to spin around it. This skater, by contrast, will grab onto the pole and they will be able to continue around it because they are maintaining their angular momentum. They have angular momentum of magnitude r cross mv. There's their mv vector. R cross p is the angular momentum. So as long as there's no external torque, the object will maintain its angular momentum. So let's go ahead and select all this stuff here. As long as the object will keep its same angular momentum as long as there's no external torque. Skater 2 can grab the pole and maintain angular momentum because there's no torque on them. Notice that when they grab right there, the force on them is perpendicular to their velocity. So their force this way is going right through that axis of rotation. It will not exert any torque about that axis. They can just maintain that. So here's a question for you. Let's say I apply a linear force to the right. So I push this skater to the right or I push this skater to the right. Does either of those forces supply a torque
about the pole
to either skater 1 or 2? So if I push this skater to the right with a force or push this skater to the right, well, what's the moment arm? If I exert a force this way, notice that my force vector or the line of action of the force goes right through the axis of rotation. A force this way will not add any angular momentum. Exerting a force this way, the line of action of that force is some distance d from that axis of rotation. So yes, I will exert a torque.
For skater 2.
Moment arm will be the shortest distance to the line of action of the force, right there, and that's that d. So the moment arm for exerting a force on skater 2, that way, is d. Moment arm for skater number 1, if you exert a force that way, notice no torque, moment arm is 0. Let's look at one other angular momentum conservation situation. The situation where we have a planet or a comet orbiting around the sun. In this case, angular momentum is conserved, but again, it's angular momentum of a particle. So let's first ask why. So let me just show you the situation we have here. This is the situation in which we have a particle or a comet right there, and it's orbiting around the sun in an elliptical path. Specifically, we really love to look at it at 2 different points. One is called perihelion, where it's near the sun. The R value is minimized. And aphelion, where it's the maximum distance away from the sun, and the R value is maximized. Reason those 2 situations are good is because the angle between R and the momentum is always a right angle right there. That's a right angle, and that's a right angle. Again, you got to put them tail to tail, so I'd have to actually put R out here, R min right out there, and R max right out here. But given that, it's still a 90-degree angle. Okay, so now one thing, that little mnemonic to remember, perihelion. Per sounds like, it means near, and it sounds like it too. Perihelion, near a helion. Aphelion is away. A for away. That's when it's farthest away from the sun. Now, why is it that angular momentum of the comet and sun system is conserved? That is because, let's look at the R's and F's involved. So here's an arbitrary point where the comet's at. Which way is R? Here's R right here. Let's go ahead and draw it in red. R is the displacement from the axis of rotation to where the mass is stationed. There's R. And now, which way is F? Well, of course, the force on this thing is that away. That's FG right there. What is the angle between R and FG? It is 180. What's the sine of 180? It's 0. A central force can exert no torques. Any central force, like a sun pulling on a planet or a comet, can exert no torque. So if there's no external torques on the system, there's no internal torques for that matter, that means that angular momentum is conserved. So, and we can just look at the comet and just say its angular momentum with respect to this axis of rotation right there. In fact, I'm going to just put a little star there. It's our center of our axis of rotation. So that means that L initial will equal L final. So L initial equals L final. That means that the radius at perihelion times the mass times the velocity at perihelion will equal the radius at aphelion times the mass times the velocity at aphelion. Where is it going to be going faster? Well, the mass is the same of the planet on both sides. Notice that the bigger the radius, if it's close, this is a small number. This is going to be bigger. At aphelion, this is going to be far away. A large number, this is going to be smaller. So, this will come up later, especially for the C kids when we do elliptical orbits.